Hey everyone, it's Federico here, welcome to a new video. In this video we're going to talk about this classic algorithm which is called random walk. This is kind of a staple in the creative coding landscape. So today we're going to see how we can create it. This is my flavor of it, this is just my recipe. There are of course countless of ways of doing this. This is just the way I will do it in just plain max objects without using any gen. So if this sounds interesting, keep watching and let's start. Okay, so the first thing we need is of course our jit world. Let's create one. Jit world. Let's give it the floating one attribute. Let's give it the full scale anti-aliasing, and let's also give it the ortho 2 attribute. This means that we're going to use an orthographic projection instead of a perspective projection for our rendering window. Which basically means there is no depth in our drawing. Since our random walk is going to be in 2D, 2 dimensions, we don't actually need the depth, the Z dimension, so we can set the drawing to ortho 2. This will not apply any perspective distortion to our visuals. Okay, so there we go. Let's enable the world by default, so let's give it enable 1. And let's actually also create a toggle so we can choose to turn it on and off when we want. And let's also create a jit.fps GUI to track our frame rate. So this is the jit.fps GUI object. Great. Another thing I'm going to do is to set the erase color to black. So erase color 0001. So the background of our window is going to be black. Now let's see what we want to do exactly. So our goal here is to get a point, move it to another position, let's say position 2, and then draw a line between these 2 points. Then we want to move the last position to another position, say position 3, and then draw a line between those positions, and so on and so forth. And I want that those lines all have the same length, right? So how do we move a point to another position? Well, we can do that using vectors. So we just need to sum a vector to this point, and the point will be moved to the new position indicated by our vector. So in order to do that, let's say this is our 2D coordinate system where we are moving. This is our x coordinate, this is our y. We want to generate a bunch of random vectors that go in all possible directions. But all of them must be of the same length because we want to be able to decide ourselves how long must be the step for our random walk. Cool. So let's see how we can do that in Max. Let's go here and let's create a random object that will give us a random number between 0 and 100, right? 0 and 100, because the random object always gives us values between 0 and the number that we write -1. Now let's say scale 0 to 100 between -1 and 1. So this will give us all random numbers between -1 and 1. Can test it with a bang button object, and we will see this is what we get. So this is going to represent the x coordinate for our random vector. Let's create another one, and this is going to represent our y coordinate. Now let's use a single button to trigger those 2 random values. So we can use a trigger here, bang, bang. First we will trigger the value on the right and then the random object on the left. And let's pack these 2 values into a mini list of 2 numbers, and this is going to represent our random vector. So let's visualize this with a message box, and there we go. You can see that we get 2 random numbers. Now the problem with that is that those 2 numbers are not going to give us always a vector with the same length. So these values will produce vectors that could be of all possible lengths. Some could be small, some could be very big, and so on. So what we can do with calculus to fix this problem is that we can normalize those vectors. This means that we need to divide those vectors by their length, and this will give us a vector with a magnitude of 1, which is always going to be the same length. So normalizing means that we need to take the vector component and divide it by its magnitude. This is the symbol for the magnitude. This is its length, basically. Sorry, this is what I wrote, length. So we divide each one of the components of the vector by its magnitude. So this is going to be x divided by the length, and then y divided by the length. So how do we calculate the length of the vector? The length is simply calculated as the square root of x squared plus y squared. This is basically the Pythagorean theorem, because if we are in a 2D space, and this is the x component of our vector, and this is the y component of our vector, and this is our vector, we can think that this is the hypotenuse of a right triangle. So in order to calculate the hypotenuse, we simply do exactly that, x squared plus y squared, and we get the square root of that. So that's exactly what we need to do. So let's go in max and do that. So in order to get the length here, we need to get the square of the x and y. So we can do something like that. Then we sum these two numbers together. And then we get to the square root of that. So square root. And this should be it. So let's see which number we get here. This is going to be a scalar number, right? So a single value. Great. Then we need to divide this vector here by the length. So this is going to be the length of our vector, or is also called magnitude, as we said before. In order to be sure that the operations happen at the correct, in the correct order, we can do this. First we trigger the length calculation, and then we send this value to the vector, to the pack object here. So we need to do that. Okay, great. So then we can use the vexp object to basically divide this list by this value. So this divided by $f2, and we want to give it the scalar mode attribute to the vexp object, which means we'll divide a list by a single value, a scalar. So let's connect this here and let's connect this there. So we are dividing this vector by that value, which should give us a vector of magnitude 1. Okay, great. And this whole operation is called normalization. We could check if we really get a magnitude of 1, basically by getting the length of this vector once again. So we could use an unpack object here, ff, and do exactly basically what we did before to calculate its magnitude. And let's check this out. Yeah, as you can see, the magnitude now is always going to be 1. So we get random vectors that all have the same length of 1, which will produce always equal steps of 1. So let's maybe let's encapsulate that into a subpatcher and call it normalize to the vector. There we go. Okay, so now we are ready to use this vector to move our points. So first we need a way to draw our points. So let's create a JIT matrix here. Give it 3 planes, float 32. And let's just give it one cell. And let's connect this to a jit.gl mesh with draw mode points. And let's make this bigger. So point size, let's say 20. And let's say the color is going to be white, and that's all we need. So let's just draw now this vector as our point in our rendering window. And let's see how this looks like. So let's say set cell 1D, cell is going to be 0, of course, because it's the only cell we got. And then let's say $1 and $2. And let's also send a bang then to this matrix. So we're going to fill this matrix with this value, since it only has one cell, and then this value is going to be sent to the jit.gl mesh. So let's see how this looks like. And there is our first point in our random walk. So now we will create another vector, and the point is going to go there. And as you can see, we are just visualizing this vector, right? We are not summing it to its previous position yet. So in order to sum this vector to the next one, so this will give us like a continuous walk feeling, we can use again the vexp object. So we can say $f1 plus $f2. And $f1 is going to be the new vector, and $f2 is going to be the old vector. So in order to store the old vector, we can use zl register, I think this stands for, which means whatever list comes inside is going to be stored inside the zl object. And then when we want to output it, we just send a bang to the zl. So let's give it a try, send a bang here, and then I try to output this list. But this will not work because the vexp object needs a default value. So what we can do is to just give it a default list of 0, 0 at when the patch is loaded for the first time. So I guess we could do something like that. So with a load bang. So if we bang now here and then bang here on ZL-reg, you will see that it gives us the last list that was output from the Bexp object. And then we can use the vector from the previous step to sum it to the vector for the new step. So we will do something like that. First, we will trigger the list from the previous step here. And then we will send the list for the new step here. And let's see what comes out of here now. Let's close that. Great. We are keeping on summing those vectors. So as you can see, they keep on growing and sometimes they shrink because the previous vector was negative. Okay, this is great. The only problem is that these vectors are just too big, right? A vector with a length of 1 in our virtual world, where a length of 1 is a pretty big number, is simply too big. So what we can do is to reduce the length of this vector by using again the Bexp object. And we will say $1 multiplied by $f2. But $f2 is going to be a scalar, so a single number, so we need to say scalar mode here. And so let's connect these here. And this is going to be the length of our step. So this is going to just be a number that we decide. Let's load mass it at 0.05, for example. So the vector is going to be multiplied by 0.05. And this is going to be a much smaller step. So as you can see, we already have some sort of random walk. And of course, I forgot, we don't have to connect this set cell to that object. We need to connect it to our final here Bexp object, which is the final output. Silly me. Hopefully this was not too confusing. So let's try now. And as you can see, I sent this vector out, but was just too big, so the point went out of the window. So in order to reset this wall random walk, let's create a bang here, and let's call it like reset, and then let's send out this reset bang. And what this will do is that it will set this list to 0, 0 here. And we'll also set this one to 0, 0, just to be completely sure. I think this is it. So let's give it a try. And let's start. Okay, so cool. This is now working. We have our random walk going around like a drunk person in our rendering window. Cool. And now we just need a way to record the steps our drunken point did. So we could do it by using vertices, so keeping on adding vertices to this matrix. But this could result in an unknown amount of vertices, right? This could be millions of vertices. We don't know how many steps our random work is going to do before we stop it. So we will use another approach, which is to keep track on the steps on the pixel level. So we will keep the pixels where the point was white, and we'll accumulate this color at every step. So in order to do that, we're going to use a jit.gl.node with the capture one. We're going to call it node, walkie node. And if you don't know how the jit.gl.node works, there is a video I made about it. There is actually several videos I made about it. I will put links in the description. So if you're confused by that part, go check them out. Basically, what this will do is that it acts as a render target for our jit.gl mesh if we give it the name of the node. So let's give it here walkie node. This is going to be the render target now for the mesh, which means the mesh will not appear anymore in the rendering window, but will appear inside this P window, inside the texture output by the jit.gl.node object. So as you can see, there it is. But we still want to visualize it in the main window. So what we can do is to use a jit.gl video plane with transform reset 2. And this actually will draw to our main window. So as you can see, there it is, our little point. We can also give full-scale anti-aliasing to the node itself. So what we want to do now is to continuously accumulate those pixel values. And we can do that with a jit.gl slab shader, which is called coaccum.jxs, I believe. So if I double click on this jit.gl slab, you will see that it gives us this shader file. Which is great. We can use it to do exactly that. As you can see, it's mixing between the previous texture and the next texture using a raise color alpha value as a mixing value. So let's see how this actually works. So we need another texture that will work as our accumulation texture. So let's create another jit.gl texture here. So this goes here, the output goes to this other texture, and the texture goes as the input for the next frame. And we also need to set the erase color attribute of this slab file. So param erase color to 0, 0, 0, 0, 0, and 0 for the alpha. That's very important. And this should be it. Now we should be able to accumulate the pixels. And as you can see, it's working. So we got here our random walk in our rendering window. Instead of me clicking, let's create a QMetro object or a metro object, doesn't really make much difference, and let's connect it to the trigger bang bang object, and let's activate it here with a toggle, and we will see our dot starting to crawl in the window. And we can make this go faster if we set a lower value here for the metro. There you go. Okay, now if we want to erase this whole thing, it's not enough anymore to just erase the list there. We also need to erase this texture. So what we can do is to send to this texture, our accumulation texture, an empty matrix. So I will just send a JIT matrix with nothing inside to this texture. And this should erase these. Since this matrix is just full of zeros, this will erase that texture there, right? There we go. Texture is gone. Let's try again. And nice. Now, the only thing I want to improve about that is that I don't want to render these as points, right? I want to render these as lines. So I wanted the point from point 1 to point 2, it's drawn a line and so on. So I don't want to just have the points, I want to have the line in between. So in order to do that, we need to have a matrix with at least 2 cells, right? Because a point is made of 2 cells. And in order to do that, what I thought is that we can use the jit concat object, which will just concatenate 2 matrices one after the other. So if we give it 2 matrices that have both a length of 1, this will give us in output a matrix with a length of 2. So what we want to do is to concat the matrix from the previous step, the matrix containing the previous step, to the matrix containing the new step. So what we can do is something like this. First we bang, let's delete that. So let's do like this. First we bang the old matrix out, then we send it to the current step, and then we send the current step to the jit concat. And we also need to set this to true 0, otherwise this matrix will output a matrix every time it receives a new matrix. So what is happening now, and let's see, we can see that probably with jit window. This actually, it's not the best tool because these values can be negative, so we don't see them. So let's actually use the jit cell block. And let's see, before here the x value was minus 0.07 and here was minus 0.05. When we trigger the next step, we should see that this becomes minus 0.07 on the right, exactly. So this becomes the previous step and this is going to be the new step and so on. The step on the left always becomes then the step on the right. Okay, it could be done in thousands of different ways. This is just the way that popped to my mind first. Now to have the final effect, we need to set the draw mode to lines or line strip actually, instead of setting it to points. So let's reset and let's give it a try. And as you can see, it's drawing adjacent lines and doing the random walk. Awesome. The time for the step should never be smaller than the time necessary to render a frame, otherwise this step will not be accumulated on our node. Exactly. So you can see if I set the time to 2, for the QMetro, this will not be enough for the node to draw those steps in the texture. So we always need to set it to something bigger than the time between the frames. So cool. As you can see, when I reset, the line is going to start from the last position where it previously was. So what we should do is when we reset, we should also set all to 0 here. So let's do something like this. Set all 0 for that matrix and probably also that matrix, why not? So let's give it a try. And there we go. Now it will always start from the center of our rendering window. Nice. We could set our line width to something a bit bigger if we want. So line width 2, for example. This will give it a thicker line. And we can choose the size of our step, right? So if we want to have very small steps, we just need to modify this value here. This is our step size. And all the steps will have the same size. So this allows us to have a lot of control. Let's delete that. Let's delete this bang button here. We don't need it. And cool. This was my tutorial on random walk. I hope it was not too confusing. I hope you liked it. And if you liked it, please gentle caress the like button, give a gentle push to the subscribe button, and you can get the finished version of this patch on my Patreon. In this way you will also support the channel and support the creation of all my videos. So very much appreciated if you choose to do that. So this was it. I wish you a beautiful end of year, if it's the end of the year in your part of the world, and I will see you in the next video. Have fun and take care. Ciao.